So in this particular lecture, I think it will take us about an hour or so. We are going to cover the same material, output determination models, but using the mass approach. And these are this particular presentation will include several questions, worked examples, which will come up in your assessment. So there will definitely be some questions in your test, which will include the exercises based on this material. You can be asked to calculate equilibrium quantities or prices or profits for different firms which operate in different types of oligopoly. So depending on what solution you are asked to find, Cournot, Bertrand, which we'll cover next time, Stackelberg or collusive equilibrium, you'll need to solve the exercise differently. It's similar to what we've done in one of the previous seminars, where you were given cost functions and demand function, and you need to find equilibrium in perfect competition and monopoly with the same figures, right? We had to differentiate them by plugging slightly different starting formulas. For example, for monopoly, you would start with MC equals to MR. For perfect competition, you would start with P equal to MC, because perfect competition is distinguished by this feature: price is equal to marginal costs. So this is how you would differentiate the outcome, and the result will be different. Quantities, prices would be different. Same as here with oligopoly, you solve it slightly differently. So let's have a look at the process. Don't be scared. If it becomes hard, just stop me at any time. And this presentation is on Moodle, so you will always be able to come through these exercises again and just repeat step by step. So let's start with the Cournot model. So it's purely mathematical approach with no graphs. Reminder of what assumptions we've made to start with this model. It's a duopoly. In other words, there are just two companies, just two sellers from A and from B. We cannot use the color here, so we'll just use the notation A and B. Two identical firms, which means that they have absolutely the same costs and they produce identical products. There is no brand loyalty. Consumers are easily able to switch from one company to another. And for simplicity, we'll even assume zero costs. So total costs are zero, just for simplicity. In your actual test, you might be given some numbers for costs or cost function. So it's not necessarily the same all the time, but just for simplicity, let's assume this. Market supply or market quantity consists of quantities produced by two individual companies. So capital Q, which stands for market quantity, market supply, is an individual quantity produced by company A and the individual quantity produced by company B using lowercase letters. So this is how we are going to differentiate individual output and industry output. Because Cournot is an output determination model, we will first of all need to calculate the level of output which maximizes company's profit, right? And the equilibrium price will be found later from the demand conditions. So we'll have some demand function, we'll plug the quantity produced by the companies, which we find from the model, and this will allow us to calculate the prices. As before, because in oligopoly, companies are interdependent from each other, they realize that their own profit depends on their own actions and actions of their rivals. And as a result, they will act strategically. They will make decisions accordingly with potential rivals' response taken into account. The model is trying to answer these questions. Which equilibrium quantities each firm will choose to produce, apparently to maximize their profit? What will be the equilibrium price in the market? And what profits will the firms make? And we are able to answer these questions based on our particular scenario, based on our specific formulas. So let's assume very simple inverse demand function. Price is equal to 1 minus Q, and Q is the combined production of two companies. By the way, this is the same demand function which we've covered in lecture with the table. If you recall the table which we've covered 5 minutes ago, one of the final slides, this is the same demand function which we used for these calculations. You can make it more difficult, more complicated, as complicated as you like, but the process will be absolutely the same. Next, we can also denote the estimated quantity or predicted or expected quantity using this particular notation. For example, QBE with this particular notation is the quantity that firm A expects from B will supply. So this is the quantity produced by company B right? But we don't know this quantity for sure yet. We expect that company B will produce this quantity. And likewise, this particular notation, QAE, will denote the quantity produced by company A, which we anticipate. So we are rivals for company A, and we expect that they will produce this amount. So these are expected quantities, right? Some notation. Next, profit function. As before, we've covered this previously, so this should be familiar to you already. Profit function, capital Pi, for any company can be calculated as total revenue minus total cost. Total revenue is price times quantity for both companies, any company, A or B. So I here is the symbol, which means that it applies to any company. So no matter how many companies we've got, each company will determine their profit in line with this formula. Total revenue, price times quantity, minus total cost. Next. First of all, for Cournot model, we'll need to find the reaction function, because Cournot equilibrium is the point where two reaction functions cross. So we'll need to find the formulas for reaction functions, formulas which describe this line. As we've covered in the lecture, in the first part of this material, reaction functions describe what level of output each firm needs to select to maximize their profit, given the expected output produced by their rival. So let's consider this problem from A points of view. The optimization problem can be recorded like this. Company A tries to maximize their profit, which is equal to total revenue minus total cost for company A. So it's price times quantity produced by company A minus their costs. We know from our assumptions that costs are equal to zero. This is what we've assumed, right? Just for simplification. This means that we can actually get rid of this particular term in our profit formula. In other words, our profit maximization can be recorded in a slightly simpler way. We maximize our profit, meaning that we maximize just our total revenue. There are no costs, so it's sufficient for us just to maximize revenue. And our revenue is price times quantity. Price is, of course, the market price, because we cannot really separate our market into individual demand curves. It's a market price determined by the demand condition, but our profit depends on our individual quantity, right? Now, let's develop this formula. Let's plug in other information which we have from our exercise, from our example. We know from our demand function from the previous slide that price is equal to minus Q. So this is the demand condition, which shows the relationship between price and quantity. The higher the quantity, the lower the price is going to be, and vice versa. Inverse demand function, standard demand function. So we can replace the price in our profit maximization formula with this expression for price, right? It's 1 minus Q. QA remains the same, unchanged. So we've just replaced the price. Next, we also know that market quantity, market supply, consists of two elements. So this is our first assumption, again, from the previous slide. Market quantity is a sum of individual quantities produced by two firms. So we can replace this capital Q with this expression. So for company A, we expect that company B will produce this amount, plus our own output will give us combined market output. So our formula for profit will now look like this. Are you okay with that? Are you still following?
Yes.
We just plugged all information which was given. Next. Now we'll need to expand this formula, open the brackets, just multiply, bring QA in. And if we do so, we multiply 1 by QA, so we are going to get QA. Then we multiply QA by this expression in brackets. So the whole formula will start to look like that. So we just bring QA in, multiply by 1, and put it there as well. And next, we open these brackets inside now. So we'll have same QA, right, minus QA squared, right, minus QA times QB, right? So this is our expression for profit now. And now we can see that our profit for company A, remember, this is profit for company A, it depends on our own output, right? So it depends on QA, QA squared, but it also depends on quantity produced by our rivals. So our profit depends not just by our output, but output produced by our rivals. So this is a mathematical proof that we'll need to take our rivals' quantity into account when maximizing our profit. We don't just depend on our own actions, we depend on our rivals' action. And the same is true for the second company, for company B, because they're facing the symmetrical situation, so they will have absolutely the same outcome, right? We cannot influence company B output, we cannot affect QB production level, but we can adjust our own QA, right? So we'll need to figure out what we'll need to select in order to maximize our profit, given our expectation of what our rivals will produce. Both companies are facing absolutely the same scenario. Both will be dealing with the same problem. We don't know what QB is going to be, but we'll try to do our best given our certain expectations. So we have the profit function, which we'll need to maximize. From the previous lectures, we know that to maximize a function, we use first order condition. So we'll need to take a derivative of this function to our variable of choice and set it equal to 0. So we differentiate our profit function with respect to quantity A. This is our profit. This is our company. We are trying to maximize our profit by varying quantity A. That's why we differentiate it with respect to QA. Let's take a derivative. Derivative of QA with respect to QA is unity. Derivative of this term, Q squared, is 2QA, as we've covered last time, right? And when we differentiate the last term, QA, QB, it becomes just QB, right? So this is based on rules of differentiation. See it. If you struggle with this, in the last week, I've created a separate set of slides which gives you a review of calculus, and all of these rules are covered there. So if you don't follow this logic, if you are unable to differentiate this yourself, or if you've done a mistake by differentiating this, when you will be preparing for the exam, you will do some exercises at home, right? If you struggle with differentiation, you can refer to this set of rules from the previous lecture, calculus revision, right? So first order conditions. Girls, are you okay with this? Because we've worked with you in the last couple of weeks on this. Yeah, are you okay with that expression?
Yeah. Yeah.
Yeah, I think you were fine. You were able to differentiate it with no issues. Right, so we've differentiated this, and in line with the first order condition, we make it equal to 0. Now we need to solve this equation, right? We'll need to work out the best response function. So in other words, we'll need to find what is the expression which describes our QA. We'll need to calculate. Yeah, sure.
You see when you differentiate
Yes.
QA, why
Yeah.
is it 1 and why is it 1 and why doesn't it disappear instead?
This one.
Yeah.
Because if you differentiate any x, it's equal to unity. Any variable, when it's differentiated with respect to itself, becomes a unity. Yeah.
Okay.
So because we differentiate this term with respect to itself, it becomes into unity. So x basically describes any expression, any formula, any unknown. So in this case, our x is QA. When we differentiate this expression with respect to QA, it becomes unity. So this term is equivalent to x squared. It's our variable squared. And if we differentiate any squared variable, it becomes 2x. So it becomes 2 times the variable itself. So it becomes 2 times the variable itself. QA is our variable. This is equivalent to situation when we have some constant times x. So some number, some unknown constant times our unknown. And when we differentiate this, it becomes equal to this constant, right? Whatever the constant is. In this case, QB is the constant. QB is our constant and QA is our x, is our unknown, is our variable in question. That's why when we differentiate this, it just remains the constant. You see, QA is our x, is our variable, it disappears, and whatever will be left will be QB, is our constant. Yeah, so these are the set of rules. Do you see it now? Yeah?
Yeah.
So whatever whatever we have here, so if we look at this one, right, if this is probably the hardest. So basically, this is our unknown. So imagine that this is x. It's the same as x. This is our unknown, right? And whatever is left, whatever is after this, whatever else we're adding, which is not x, is equivalent to constant. So basically, it's just another notation for the same expression. We multiply the unknown, the variable in question, times some number, times some constant, right? And when we differentiate this expression, it simply becomes a constant, right? It disappears. Yeah, it's the same like it would be 5x. If we've had 5x, we've differentiated it with respect to x, it would become 5. Oi, sorry. Go back. Where we are we? Here. No, we're here. I've lost where we've been. 1 second. I think it's stuck. Slideshow. It's a bit stuck. You know what? Let me just close this and reopen again. I think it's not doing something correctly. Here it is. Cube. Let me just reopen it again. Here it is. So it's something like 5x or any other number times our x. If we differentiate it, it will be equal to 5. It will be equal just to this number. So x will disappear as a result of differentiation. Our unknown will disappear, and whatever number we multiplied by our unknown will still remain. And in this case, our unknown is qa. It will disappear, and only the second part of this expression of this term will be left. So it will be qeb. Okay? Yeah, is it better now?
Yeah.
Yeah, hope it's okay. Probably you need to do a bit more practice. So if you cannot follow this naturally, have a look at some from past weeks, some math exercises. Just do a little bit more practice so that it becomes more natural for you. But we just differentiate. And in reality, the chances are you might get this in the test because some of the questions ask you to derive the reaction function. So you might be asked not to calculate quantity, so you don't complete the whole model in the test, but you can be asked to derive the reaction function. And this is how you do it. It's basically this particular slide. So differentiation is important. So just do a little bit more practice, refer to examples from the slides on calculus revision as well, so that it becomes more natural for you. So we've taken a derivative, made it equal to 0, right? And next step, what we have to do is just to work out QA from here. So from this expression, we just solve it to find QA. From this expression, we move all terms with QA to one side. So 2QA, we move it to the right-hand side, right? And whatever is left will be on the other part of the equation. It's 1 minus QB. So to get QA from here, we just divide both this part by 2, right? So 1 divided by 2 becomes a half, and QB divided by 2 becomes a half times QB. So this expression is our reaction function. This is what we need to know. This formula will describe this particular line. So if you take individual quantity A, this is the reaction function from A, this particular line will describe this expression, this equation will describe the reaction function from A. Along vertical axis, we measure quantity B. So this reaction function, by construction, based on how we've worked out, shows what output company A needs to produce to maximize its profit. It maximizes profit because this is where we've started. We've started from profit maximization condition. We've written down the profit function, maximized it, and worked out our quantity. To maximize our profit, we produce this quantity for each possible quantity B. So whatever our rival is producing, there is the best response for us. So no matter how many units they're doing, we know how many units we need to do to maximize our profit. For example, if they produce, for example, I don't know, 10 items, there will be some number which we need to produce. If they make 0, 5 items, whatever, 0.3, 0.5, we can calculate our best response. So for any output our rival is producing, we know our best response. And because firms are symmetric or identical, we can work out the same formula for quantity B. They're facing absolutely the same scenario. Their response depends on our actions. So if you plot the graph, company B will have a flatter reaction function B. It shows how many units company B needs to produce to maximize their profit given the production of company A. So this particular expression describes this line. It shows the best response for company B. It shows how much company B needs produced depending on what company A is doing. So this is the mathematical expressions, right? We'll need to record this. We'll need to remember these formulas. They describe these two lines, which we've used before. And again, this is the summary of what I've done. So if we've produced this best response function for company A, this is the line which can be described by this equation. The highest profit will be achieved here. This is our bliss point. This is what we called bliss point in the lecture. Bliss point, which produces maximum profit or monopolistic output. This is equivalent to monopolistic output produced by company A. Right? Highest profit. And the lowest profit will be here because this particular point means that company A doesn't produce anything. It means that company B from B is the monopolist. They produced all possible output. From B output is maximized. And because they're covering, they're serving the whole market, there is nothing for us to produce. Our output is equal to 0, and therefore our profit for company A is 0 as well. This would be the lowest profit. And if we add our isoprofit curves, they will look like this, right? The lower we are, the closer we are to the bliss point, the higher the profit is going to be. So profit is higher in this particular direction if we move closer to our bliss point for company A. So basically, this is the mathematical expression which describes all of these graphical ideas which we've covered already. So we can draw these two lines based on the formulas which we've derived, and each formula select the level of output which will maximize its profit. In other words, each company will want to be located on their reaction function, on their best response function, because it shows profit maximizing level of output. No matter what our rivals are doing, we want to be located on our best response function, because mathematically it allows us to maximize our profit. And because both firms are in the same situation, both firms are symmetrical, this is what we've got. This is the steep reaction function for company A, and this is the flat reaction function for company B. They will be in Cournot equilibrium at the point where these two lines cross, right? Previously, we've done this graphically, but now we can make it mathematically. So for each reaction function, we can solve them together. So whenever the lines cross, we can find a mathematical solution by solving a system of equations. We know the formula which describes this line. We know the formula which describes that line, which means that this particular point will belong to both lines. It sits on both lines, which means that it simultaneously satisfies both equations. It's similar to what we've done previously with demand and supply. We can find equilibrium price and quantity by equalizing quantity demanded and quantity supplied, right? So we just solved the system of these equations together, demand and supply. We've had the formula for one, formula for another, and we solved it together to find equilibrium. Same as here. We have a formula for action function 1, for action function 2. We can solve these formulas together, system of equations together, to find Cournot equilibrium, right? Two equations are solved simultaneously. So basically, we can write them down like that. Quantity A depends on quantity B and vice versa. And we simply solve the system of equations together, right? What is also simplifying thing? Previously, we based our output on our estimates or expectations of firms' production. But in reality, in equilibrium, the expectations will be fulfilled. So expected output will be equal to actual output. So strictly speaking, we can get rid of this notation now. We can ignore this notation because We're trying to find equilibrium, and in equilibrium, expected output will be equal to actual output. So this makes our life slightly easier, and our formulas will look cleaner, right? And in order to solve this, we can simply plug one reaction function into another. So to solve this, so let me just write it down for your test notes. To find Cournot-Nash equilibrium, what you have to do is simply plug one reaction function into another function into another. That's all. And solve. Simply plug one reaction function into another. So have a look. Quantity A is a half minus a half times quantity B. What is quantity B? It's this one. So we can simply plug it into our reaction function. So simply plug this expression. So we still have a half minus a half, but instead of this term in brackets, we have the expression for quantity B. And now we have a simple equation. There are lots of fractions, but they're very easy to work out. So a half is a half. A half times a half, it's 1/4, right? This, when we open the brackets, minus a half times minus a half becomes plus 1/2, right? And we still have QA. So simply open the brackets. And this is a very simple expression. Now we've got this equation. QA is equal to this amount. Simple equation with this single unknown. How do we solve it? We move all terms with QA to one side. So we take this term and move it to the left-hand side. And whatever we still left with numbers will be kept on the right-hand side. So QA minus 1/4 of QA becomes 3/4 of QA. 1/2 minus a quarter becomes 1/4. And therefore, from here, we can express QA. This will be QA becomes 1/4 divided by 3/4, right, which is the same as 1/3. And that is why I've mentioned in the beginning that we have each company produces 1/3 of equilibrium output. If you remember, half an hour ago, I told you, just remember, it's 1/3 of competitive output, 1/3. This is how we get it. Each company is identical. So quantity A is 1/3, quantity B is the same, is also 1/3. So the combined output will be a sum of 1/3, which is 2/3. What is the price? To find price, plug this equilibrium quantity into demand function. To find price, plug industry output, industry supply, industry Q into demand function. Demand function. Of course, we need to work out total output first, and then we plug out total output into our formula. Our formula for demand is this one. This is what was given to us in the exercise, 1 minus total Q, right? Total Q is 2/3, and as a result, price is 1/3. And these are the numbers which we've used in our table when I've shown you the comparison of different models. So don't be scared. It's not difficult. You will not need to repeat this whole process, and you don't need to remember it. You will have your notes with you. So all you'll need to do is just to follow the same procedure, plug in your numbers. There are some exercises online which you can try at home as well. You will need to calculate some parts of this using any data. It's not easy. So to find equilibrium quantities, you'll need to plug one reaction function in another. This will allow you to find equilibrium quantity. If you are not given reaction functions, you will need to work them out yourself by writing down the formula for profit and maximizing it. So first order condition, plug in all available data, maximize it using first order condition, and this will give you an expression for reaction function. If you have reaction function, just plug them one into another. To work out equilibrium price, you plug in the industry quantity into demand. So add up the quantities produced by each firm, individual firm. This will give you market output or market supply. Plug this into demand function. This will give you the price. If you are asked to calculate profit, just plug in this information on individual prices, on prices, individual quantities, costs if you are given, to calculate total revenue and subtract total costs, again, if they're given. Just follow the standard procedure. Right. So, for example, let's imagine that you are given the actual number. So this is the type of question which you might get in the example. Let's work through this, and you can try it home with some other exercises. This is the demand function which you are given. There are two identical firms. Each of firms have this cost function. What does this expression mean? This means that the total cost for company A is 5QA, which makes sense. Their cost depends on their own output. And total cost for company B is 5QB. Their costs depend on their own output level. Total costs. Total supply is, of course, sum of individual supply, and you'll need to work out equilibrium market supply. In other words, you are asked in this particular exercise to calculate total output. How do you do this? Let's try. So first of all, this is the reminder here at the top. This is a reminder of what information you were given. Sorry. Go back. Right. A reminder of what information you were given. These are all numbers which you have. There are no reaction functions. You need them, and that's why you'll need to work out them yourself. To do this, you write down formula for profit and then use for first order condition. So profit function. Profit function is the difference between total revenue minus total cost. Total revenue is price times quantity. So for the first company, it will be price times quantity 1. For the second company, you don't need to do this because it will be just symmetrical. You just replace the symbol. That's all. Let's do it for one company. Price times individual quantity minus total cost. This is total revenue. This is total cost. Next, what information do we have? We have information on prices. So have a look. Price is that much. So that's why we can plug this into here. We don't know the quantity, but we know the total costs. These are total costs, so we can replace this in our expression. Let's plug in these numbers. Price is 125 minus 5Q from our demand function. We still need to multiply it by Q1, by first company output. Then we need to subtract cost. Costs are 5Q1. We've subtracted them. So this first term, brackets times Q1, is total revenue. These are total costs. Let's open the brackets. Right, so what are we doing here? Quantity, we can also replace quantity with this expression. Just plug everything in. We plug this instead of capital Q. You see, capital Q is equal to Q1 plus Q2. So let's replace this first. 125 minus 5 times our industry output, which is the sum of individual output. We still multiply it by Q1. We still subtract 5 Q1. Okay? Next, 125. Now we open these squared brackets, right? 125 times Q1, 125 Q1. Next, we open all of these brackets straight away. Minus 5Q1 times Q1 will become 5Q squared. Okay? Next, 5 times Q2 times Q1, and we have a minus here. So minus 5 Q1 and Q2. This is what we've got. And we still have this term, minus 5 Q1. Okay? We've just opened the brackets. Now we can simplify because we have 125 Q1 minus 5 Q1. So this and this. We can subtract one from another for slight simplification. So we're left with 120 Q1 minus the rest. Next, this is the expression for profit. Now we can maximize this profit. We cannot simplify it. We cannot plug anything into this. And this expression actually tells us that profit is our profit, and it depends on our own output, Q1, and rivals output. Exactly what we've tried to state in the lecture, and rivals output, Q2. We cannot control Q2. We take it as given. We assume there will be some number. We don't know how much, but we can try to adjust our own output Q1 to maximize our profit. So let's work out how we can do this. Maximize profit using first order condition. Because our variable of choice is Q1, we differentiate with respect to Q1. Remember, in this case, using rules of differentiation, Q1 becomes our X. So for differentiation, Q1 is our X. The rest are constants. The rest are our constants for rules of differentiation. That's why if we take the derivative of this, what do we have? We have a constant times our variable, 120 times x, basically. And if we differentiate it, we'll only have 120. When we differentiate this term, it's basically equivalent to stating that we have this expression 5x squared, and when we differentiate it, we basically drop our power and it becomes 10. 5 times q, 5 times 2, 10 times our unknown times our x times our quantity. So we've got this expression, and when we have this expression, this one, it's equivalent to writing something like this: 5 times x times some constant, some unknown, some constant. And when we differentiate it, when we take the derivative of this expression, what will be left? X will disappear and we'll have only constants left. So it's 5 times our constant, 5 times Q2, 5 times Q2. This is the derivative. We've differentiated the profit function. We've got this expression. Now we need to make it equal to 0 and solve. So we set it equal to 0, and this is what is left, and we'll need to express Q1 from here. We need to solve for Q1. We'll need to figure out what Q1, our output, we'll need to select to maximize our profit. So we'll move all terms with Q1 to one side, all other terms to another side. We have this expression, and now we solve it for Q1. We need to divide each of these terms by 10, and we are left with this specific expression, 12 minus a half times Q2. So this is our reaction function. This formula will describe this particular line, reaction function for company A, for company 1, which shows how many units quantity company 1 needs to produce for any quantity produced by company 2 to maximize their profit. Right? And because the companies are symmetric, so this is what we've got, because the companies are identical, they will have absolutely the same reaction function. So this is reaction function for firm 1, then reaction function for firm 2 will be the same. It will be 12 minus a half times Q1, symmetric. Just mirror image of this. Next, now in order to find output, we need to plug. Next step is to plug one reaction function into another. Reaction function into another. Right? So Q1 is 12 minus a half Q2. We just plug Q2 here, or because they're identical, we just replace it because they produce the same amount. We can simply replace Q2 with Q1, because this is what you can do first, or because they're identical, they are not leader follower, you can simply replace Q1 with Q2, and it allows you to solve the expression. Now we move all terms with Q1 to one side, all numbers will be left on another side. So basically 3 divided by 2 Q1 is 12, and therefore equilibrium quantity 1 will be equal to 8. So 12 divided by this. And because both forms are identical, both will produce the same amount. Quantity produced by each company will be 8, which means that industry output will be a sum of both. So it will be 8 plus 8, which will be 16. So you've been asked to calculate equilibrium quantity for the industry, equilibrium output, and this is how you do it, by creating reaction functions, right? Maximizing profit function, plugging one reaction function into another, and calculating individual quantities. Then you adapt equilibrium quantities for each company to get market supply. If you are asked to calculate price and profits, you can do this later. You can plug this into demand function, for example, price and profit. Let's do this. If our price is 125 minus 5Q, you can calculate equilibrium price. It's 125 minus 5 times 16. 16 is total output. 5 times 16 is 90, so 125 minus 90 is 35. This is the price in this particular market. And if you are asked to calculate profit, profit 1 will be total revenue 1 minus total cost 1. Total revenue is equilibrium price times equilibrium quantity for the first firm minus total cost. Price is 35, as we've just calculated. Equilibrium quantity is 8, which we've just calculated, minus total cost. Costs are given by cost function. It's here, 5 times quantity. 5 times Q1. Quantity is 8. So we've got all of the numbers. 35 times 8, 70 times 4, 280. 5 times 8 is 40, so profit is 240. And both companies will have the same profit. Profit 2 is 240 as well, because they're identical. So this is an example of how you would solve Cournot model. Next, what is this? Next example. How do you approach this differently if you ask to calculate collusive equilibrium, for example, or Stackelberg equilibrium? Let's have a look at another example. Let's imagine that there are two identical firms. Costs are the same for each company. In this case, average costs are equal to marginal cost and is equal to 10, and there are some other data given for demand, right? You are asked to calculate equilibrium quantity, price, and profit for each firm. And you need to do this for different models. So as before, you'll need to calculate quantity A, unknown in equilibrium, quantity 2 or company B, unknown. You need to calculate industry, output unknown, equilibrium price, and profits for A and profit B. This is what you'll need to calculate for all companies, and you'll need to do it in two situations, for Cournot model and Chamberlin's model. You also need to demonstrate how they have an incentive to collude and incentive to deviate. Let's do this. First of all, you'll need to find Cournot equilibrium. To do this, you'll need to write down profit functions and develop workout reaction functions. Profit function is the difference between total revenue and total cost. Total cost can be calculated as average cost times quantity for any individual company, right? Average costs are given, they are 10, and therefore total cost function can be written down as 10 times Q, individual quantity. Plug this into our profit function. Total revenue, price times quantity, minus total cost, 10 times quantity. Next, we'll need to plug in the data for prices from the demand function. We know that price is equal to 130 minus Q, right? Plug it here. So instead of price, we plug this in here, and instead of quantity, we can replace quantity with this expression. It's an individual sum of production by each company. Plug this whole expression instead of price, and the rest remains unchanged. This is our profit function. Next, let's open brackets. 130 times QA becomes this term. Next, QA times QA becomes QA squared. Next, QB times QA becomes this term, right? Next, we need to subtract 10Q, which are our costs. Then these terms can be combined together, can be simplified. 130 minus 10 becomes 120. The rest remains unchanged. Minus QA squared minus QB QA. This is our expression for profit for company A. As before, you can see that profit for company A depends on their own output, QA, and output produced by rivals, just by construction. We can simplify it somewhat a little bit here if you want to. You don't have to, but you can simplify it as well. Right, so this is our expression for profit from the previous slide. Now we need to maximize it using first order condition. Because our variable of choice is QA, this is our unknown, this is our variable which we can control, we differentiate with respect to QA, right? So basically what do we have here? QA times some number times some constant. When we differentiate this, there will be only this constant left, right? Remember, this expression is equivalent to writing something like C, some constant, times our unknown. When we differentiate it, it will become just C, just this particular constant. So just this term in brackets, 120 minus QB. When we just differentiate this expression, it's the same as x squared. When we take the derivative of x squared, it becomes 2x. So 2 times our unknown. And because it's a first order condition, we'll need to make it equal to 0 and then solve for optimal quantity. So what do we have? We're trying to find equilibrium quantity for best response quantity for company A. We take this term with QA to one side, all other variables to another side, and solve for QA. So it will be equal to 60 minus a half QB. As before, you see that optimal quantity for company A depends on output produced by company B. It's a description of our reaction function for company A. It shows how much company A needs to produce for any output produced by company B, according to this expression. This is from A reaction function. Because in equilibrium, because companies are symmetric, company B will have a similar reaction function. They will produce in Cournot equilibrium, they will produce some quantities which will be identical. So actual quantity A in equilibrium will be the same as quantity B in equilibrium. That's why we can make a simplification. We can make them equal to into each other, and we just replace QB in our formula with QA. They're identical, they're the same, and then solve for equilibrium quantity. And this happens to be 40 items, 40 units. So we now know that each company will produce 40 units of output in Cournot equilibrium, right? When they do not collude. Each firm produces 40 units, which means that the industry output is going to be a sum of these both. 40 plus 40 is going to be 80. To calculate price, plug this back into the demand function. Demand function is 130 minus industry output. Industry output is 80, therefore price is 50. Now we can be asked to calculate profits. According to our expression, profit is always the difference between total revenue and total cost. Total revenue is price times individual quantity. Total cost is individual cost per unit times quantity. Plug all the numbers which we worked out. Price is 50. Individual quantity which we've produced is 40 units each company. This is what we've calculated on the previous slide. Average cost is equal to 10. We know this from what was given to us in this exercise from the very beginning. And equilibrium quantity is 40, which we've calculated previously. When you solve for it, total revenue is 50 times 40, it's 2,000. Total cost is 10 per unit times 40 units, it's 400. So the profit of each company is going to be 1,600 pounds for both companies because companies are identical. So this is how you find Cournot solution. But you can also be asked to calculate collusive equilibrium, and you need to demonstrate that it's going to be different. So let's see if firms agree to collude, how will the solution be different and how the result will be different. As we've learned in collusion, firms act as a joint or shared monopolist. So they pretend that together they represent a monopoly. So they produce monopolistic level of output to maximize industry level profit, highest possible profit, and then share it between themselves equally, right? So basically, we look at this as from the industry level. We don't separate into individual companies. We pretend that there is one joint company in the market, one monopolist in the market. So that's why we're just looking at total output, which represents the industry output. This is the industry output or joint monopoly output. So industry output, which is the same as joint monopolist's output. Together, they are a monopolist. Next, let's plug in available numbers. Price can be described by the demand function. It's 130 minus Q. We also know that the average costs are equal to 10, as it was given. Plug this into our expressions. So price 130 minus Q times Q minus total cost, average cost 10 times Q, plug this, open the brackets, 130 times Q, then Q times Q is Q squared, minus 10Q. This is our expression for profit. We can simplify this somewhat because 130Q minus 10Q is equal to 120Q. And next we can maximize it. So this is a monopolistic profit. When companies agree to act as one, this is their highest possible profit which can be produced. Let's figure out what quantity will allow us to produce this profit. We maximize this profit using our standard first order condition method. We differentiate with respect to total quantity, right? Because this is our variable of choice. This is our unknown. This is what we can control. This is what we can vary. So differentiate with respect to quantity. 120Q differentiated becomes 120. Q squared differentiated becomes 2Q, right? And now we set it equal to 0 and solve. So for optimal Q, take all terms with Q to one side, all numbers to another side. So 120 will be equal to 2Q, which means that Q, combined total industry output, is going to be 60. And remember, it's different compared to what we've done before. If you remember what we've done for Cournot, in Cournot, each company produced 40, and together, combined as a joint production, they've produced 80 units of output. Now, if they agree to work together in Chamberlin's equilibrium, it's not 80 units, it's 60 units. So together, the companies are producing 60, which is going to be 30 units each. It's combined industry output. But in reality, they split it equally, but they don't have to. It depends on their negotiation. They can decide that company A will produce maybe 5 items, and the rest 55 will be produced by company B. Why company A might agree to do so? If they decide to share profit equally, why would you bother? It doesn't really matter. As long as the combined industry output is 60, they can share it the way they like. But assuming that they share it equally, each company will produce 30 units. So each firm will produce half of the monopolistic output for simplicity. Doesn't have to be this way, but if they decide to act absolutely in like shared way, half and half, 50-50, this is what they're going to produce. Not 40 like before, 30 only. Equilibrium market price is now going to be higher. It depends on the demand. Demand is 130 minus Q. Combined output is 60, which means that the price is now going to be 70. Not 50 like before, but 70. And each firm will make higher profit because it's a monopolistic profit right now. Profit is calculated from the profit expression, total revenue minus total cost, right? So it's price times quantity minus average cost times quantity. Let's plug these numbers in. Our price, which we've just calculated, is 70 pounds. Our quantity, which we've calculated on the previous slide, is 60 units for the industry. We are talking about joint profit, industry level profit. Average cost per unit is 10 pounds. We are making 60 units, which means that our combined joint total revenue is 4,200. Total costs between two companies for all production is 600. So total profit is 3,600. And now we can share it equally, which means that each company will make 1,800 pounds profit. Again, if you put all of these numbers together from both models with no collusion and with collusion, you can see how the outcome is different. In Cournot model, each company produces 40 units. Now they're producing 30 units only. Like any monopolist, they're cutting down, restricting their production. So the whole industry supplies not 80, but 60 units right now, much lower total output, exactly like monopolists, what they're doing. Because they're producing lower output, the price is now going to be higher, 70 rather than 50. And each company's profit is now going to be high as well. So they have an incentive to collude. They have an incentive to restrict output and elevate the price because it allows them to achieve a higher profit. In Cournot, they would get only 1,600, but now they're getting 200 pounds more. They have an incentive to do so. Okay, why collusion is unstable? We've shown it in a graph. Because in a graph, I've demonstrated that collusive equilibrium is outside the firm's reaction function. They are not on individual reaction function, and as a result, their profit is not maximized. So firm 1 has this reaction function. Firm 2 has this reaction function. This is quantity for company A. This is quantity for company B. In Cournot, they would be located here, but joint equilibrium, joint profit maximization is some point on this dotted line. So somewhere here. And point J implies that they're producing less output, monopolistic output for company A and monopolistic output for company B, joint profit. Joint profit maximization output. They're located here, but point J does not sit on any of the reaction functions. It means that individually each company could do better by moving to their own individual reaction function. Company B would be better by moving to this particular point. Let me just do it this way. So company B would prefer to be here and company A would prefer to be here. So strictly speaking, they would prefer to move to these points. And they have an incentive to deviate, to vary their output, to increase production. They understand that they're now doing the best they can, but individually they have an incentive to deviate, to cheat and produce more than their agreed quota. So let's have a look at the proof. So this is for individual company, right? Our individual marginal revenue is not equal to individual marginal cost. Let's have a look. Total revenue is price times quantity. According to the demand, price is 130 minus Q. If we multiply it by individual quantity, we will be able to work out marginal revenue for the company. What we are doing here, we're trying to demonstrate that individual marginal revenue is not equal to individual marginal cost. You know what? Let me just erase. One second. Let me just erase this so that it doesn't clutter our slide. Have a look. We are not on individual reaction functions. This is the graphical proof, but mathematical proof of showing why this is a suboptimal equilibrium for individual company is to demonstrate that marginal revenue is not equal to marginal cost. This is what we're trying to show. To calculate marginal revenue, we need to differentiate total revenue, and this is exactly what we're doing. We take total revenue. This is our expression for total revenue. Price times quantity. Price is taken from the demand function. We replace quantity with the sum of individual quantities and then open brackets. This will give us an expression for total revenue, right, for company A. Then we've rearranged it. And now we can calculate marginal revenue. To calculate marginal revenue, you know that it's a derivative of total revenue. We differentiate it with respect to QA, and this is what we'll get. As a result, marginal revenue can be described by this expression, right? Now let's plug in the numbers. In our collusive equilibrium, if we produce the quantity we agreed, 30 units each, our marginal revenue for company A is equal to 40 pounds. So 130 times quantity produced by our rival, 30 items, minus 2 times our quantity, 2 times 30, makes it 40 pounds. Our marginal revenue, according to marginal revenue function and actual production levels, is 40 pounds. At the same time, we know that marginal cost is equal to 10 pounds. This is what was given to us. So this situation is suboptimal. Marginal revenue is not equal to marginal costs. In reality, right, this is our scenario. To maximize our profit, they need to be equal, but they are not. Moreover, marginal revenue is greater than marginal costs. In other words, in this situation, if you just look at these numbers, in this situation, you produce certain level of output. But marginal revenue, in other words, additional revenue of producing an additional level of output will be equal to 40 pounds. If you increase production by one item, your revenue will increase by 40 pounds. So if output produced by our company goes up by 1 unit, if we produce just 1 extra unit, total revenue goes up by 40 pounds. We gain 40 pounds. This is what marginal revenue equals to 40 means. But at the same time, total cost will go up as well. It costs us some money to make this item, but it will go up by 10 pounds only. So we have a gain of 40 pounds and loss of 10 pounds. What is the net gain? 30 pounds. Net gain plus 30 pounds. we will be better off by 30 pounds if we produce one extra unit. So this situation, when marginal revenue exceeds marginal cost, implies that we are better off by increasing our production. It will allow us to earn even higher profit. That's why we have an incentive to do so. We have an incentive to produce output. And because they're identical, they have absolutely the same incentives. They act in absolutely the same manner. They both have incentive to produce more. In both of their situations, marginal revenue exceeds their marginal cost, and as a result, they do so. As both companies increase their output, this leads to instability of this equilibrium. A collusive equilibrium does not hold. It's not stable, and eventually the industry will just converge back to Cournot, because then companies just stick to it. They don't have an incentive to cheat or deviate from it. So this completes this second set of slides. Again, it's probably the hardest part of the module, but we're done. We're finished. And in your seminar, in your test, you'll just need to complete the process. Try to do some homework exercises. Just download them. I'll make them visible this afternoon. Have a look at them. Try to practice. If you have any questions, approach me during the next class. But in the test, you will just need to do the same. Bring your notes with you, just plug in your numbers and follow the same logic. You don't need to remember all of the steps, just repeat the process with your fingers. This is all you'll have to do. Any questions?
No, thank you.